Our paper presents a generic language for creating MDD propagators. This work was done in collaboration with my advisor, Laurent Michel, and with Willem van Hoeve. In the past, MDD propagators have been developed that, for some cases, can achieve orders of magnitude speedup compared to conventional domain propagators. However, these implementations have different designs and are dedicated to their specific constraint types. But they do share some similarities, and this has led us to create a generic language and architecture for MDD propagators. With HADDOCK, we can develop, combine, and evaluate MDD propagators much faster than before, and it is seamlessly integrated into a generic CP solver. We'll start with a refresher on decision diagrams. We'll go over the different elements necessary for our language. We'll show how those elements work together in the implementation, and then we'll wrap up in the results. Decision diagrams are a way of graphically encoding all solutions for a set of constraints. If you start with the full MDD for your variable set, and remove any arcs that would be infeasible for your constraints, then what you're left with is a graph where every path from the source to the sink is a solution to your problems. Relaxed MDD set a maximum width. If any layer would have more nodes than that width, then those nodes are merged together such that you might introduce new infeasible paths, but no feasible paths are removed in the process. CP traditionally propagates on only conventional domain stores. MDD propagators take this and expand, propagating on both a conventional domain store as well as on an MDD. But it's not always clear how we get an MDD propagator, and again, this often has involved writing dedicated MDD propagators for that problem. There are three forces at odds with each other when creating this generic language. First is, well, we want it to be generic. We want the MDD propagators to be reusable, and we want them to all behave similarly. We also want it to be customizable. We want to take those individual propagators and tweak them for performance using different heuristics. And we want on the outside it all to be easy to use. We don't want it to be a headache to create an MDD propagator. And at the center of all this, we propose HADDOCK, which stands for Handling Automatically Decision Diagrams over Constraint Kernels. Our goal with HADDOCK is to be able to write an MDD propagator model in the same way that we might write a CP model. If we start with a problem, writing a CP model starts with creating your CP solver, taking any parameters you need, and then creating the variable arrays and adding to that CP solver any constraints necessary on those variables. An MDD propagator can follow a similar structure. You would still use a CP solver and your variables, but you introduce an MDD propagator that has a maximum width, and instead of adding those constraints directly to the CP solver, you add them to the MDD propagator, and then add the MDD propagator to the CP solver. So, now that we've shown where we're trying to go, let's show how we get there. When we start with a model, we break it down into all of the constraints necessary. Each of these constraints can correspond with an MDD specification. These specifications give the set of rules or guidelines for creating an MDD for that constraint. So an MDD specification for just an all different is everything you need for creating MDDs for that all different. And these MDD specifications will vary based on the constraint, variables, and parameters necessary. Then, we want to be able to take all of those MDD specifications and get their conjunction. And this MDD specification would represent the MDD for the initial model. This MDD specification can be used by an MDD propagator. So the first question is, what does an MDD specification look like? The building block of this language is states and their properties. Every node in the MDD will have a state, and each state is composed of different properties. These properties describe all paths on the MDD from source to sink that use this one node. So, we often break this down into prefix and suffixes of the paths with respect to the node. In the example of an among constraint, we would have two properties, L down and U down, that represent the minimum and maximum number of values on paths in the MDD from the source to this node that are in S. If we look at an example in this MDD, we can see that going from the source to this node, there's a minimum of 1, 1, as well as a maximum of 1, 1. So our L down and U down are 1 and 1. We also have L up and U up, representing the number of values and paths from the node to the sink. And we can again see that we have a minimum, this time of 0 ones, and a maximum of 2 ones in those paths. So our L up and U up are 0 and 2. The next question is, how do we get these values? And we do that with transition functions. These are passing the properties through the MDDs, updating them, going either forward in the MDD from parent to child, or in reverse from child to parent. If we look at that among example again, the L down and U down of a child node can be set to the L down and U down of the parent, plus whatever the arc that connects them, if that value is an S. So we can just take the L down and U down of the parent, add if V is an S, and that is our new value for the child. And the same thing just happens in reverse for the L up and U up. The child's L up and U up are passed upwards to the parent node, and the parent node can update their values to Y plus 1 and Z plus 1 in this example. Notice that we don't have forward and reverse transitions defined for every individual property. We only have them when necessary. But we want to be looking at this state level. So to combine them all together, we use state transitions. This will group together all of the property transitions useful in that direction. And if there aren't transitions defined in that direction, then it just leaves them untouched. So this lets us call this down transition, this forward transition function for the state to update the states of a child based on the parent state, or in reverse, updating the state of the parent based on the child state. The next challenge we have is that because it's relaxed, there will be cases where one node will have 2 arcs pointing to it, and it's not clear how we can combine those transition functions together. And for that, we define relaxation functions. And again, we break it into property relaxations that return what the new property value should be based on the relaxation of those 2 states, and state relaxations that combine together all of the individual property relaxations, so we can just call that one state relaxation function to combine those 2 input states to get a new state. Because it's a relaxation, it's going to often be either a minimum or a maximum. In the case of our among example, we take the minimum of the lower bound properties and the maximum of the upper bound properties. Also, because we take as input 2 states and return one new state, we can, if we have any number of incoming arcs with their own states, then we can just pairwise call the relaxation function until we're left with only one state, and that state would represent the relaxation of all of the initial states. With all of this, we have what we need to get the states defined in every node in our MDD, but we're not doing anything with that information yet. So, if you think back, we had our full MDD and we removed infeasible arcs. So with that, we need a way to remove those arcs. We call transition existence functions for that. And this is a function that will take the states of the parent and child of an arc, as well as the information about the arc itself, and return true if that arc might exist on some feasible path in the MDD. In other words, if that function returns false, then we know that arc will not be on any feasible path, so we might as well delete it. In the example of the among constraint, we can return false, so we can delete the arc if the lowest possible valued path that uses that arc has a value greater than the upper bound, or if the maximum possible value of a path that uses that arc is less than the lower bound. Because in those cases, we know the constraint's going to be violated, and so we might as well delete the arc. And with all of this, we have what we need to create an MDD specification for just one single constraint. The next question is, how do we combine them together? If they have the same variable set, it's fairly straightforward. The 2 MDD specifications would have their own properties and transition functions, as well as relaxation and transition existence functions. And so when we're creating our new MDD specification, well, the variable set is still the same, but we can concatenate together the properties, transitions, and relaxation functions because we're going to need all of that information in our new MDD. The transition existence function is a little different in that we combine that together, we take an AND of them, because if either one of the initial MDD specifications If either of the initial constraints would delete that arc, then we want to delete that arc. If they have different variable sets, it's slightly more complicated, but the main thing is that we're adding in new variables in the final MDD specification that were irrelevant to one or more of the initial specifications. This means that our MDD will have layers that are completely irrelevant to some of the specifications that we started with, and we want to sort of skip over those layers. In the case of transition functions, we will copy the value from parent to child or child to parent in the case of reverse functions. And for existence functions, we will call them only if it's a layer that is relevant to that variable, or the variable is relevant to the constraint. And with all of that, we can now have our language. So how does it work in action? Well, let's say an external event would tell our MDD propagator that a value has been removed from a domain of a variable. The MDD propagator would pass that and use that to remove arcs from the MDD that violate that rule. That would then trigger internal event. It would trigger that an arc has been removed, which means we want to schedule the parent and child of that arc for consideration. When we're considering this state, we want to recompute its value. We will call the forward and reverse transitions on that state and relax them together to update what that state should now be. And if that state's value did get changed, then we'll want to call the existence functions on all arcs going into and out of that state to make sure they're still feasible. And we'll also schedule that state's parents and children for consideration. When we're considering those states and updating their values, we take advantage of MDDs being Berger cyclic. So we update nodes topologically, going in a forward queue from the source to the sink, and a reverse queue from sink to the source, only updating nodes that are possibly changed, and we can repeat this until a fixed point is reached. To show an example of all this in action, we would start with an MDD specification. It has its variables, properties, and all of those functions we defined. The variables by themselves can be enough to build a full MDD with every variable corresponding to a layer. The properties we define can be used to set the default states of the source and the sink nodes. And then all those functions can be slotted into the MDD propagator's rules so that it can use that MDD specification. This propagator can now propagate on the MDD. And it will do that by doing a forward pass, calling the forward to queue rule. And as it does that, it will update states. It will split states, which will also be updating the state. It will then, whenever a state's updated, go over all of the arcs, see if it can delete any. If so, it would call the arc deletion rule. And this whole process just continues down the MDD in this forward pass. It would then, once it has finished that forward pass, it would do the reverse pass, just going the other direction. And this whole time, if an external propagator were to remove a value from a domain, we would call the domain changed rule. So let's get into the results. We tested our HADDOCK language with the classic nurse rostering problem. Our goal with testing was to see how HADDOCK compares against the classic implementation of the model, so the conventional finite domain model. Our hope was that we would obtain a speed up similar that the dedicated constraint gets, that the dedicated MDD propagator would get. We expect that the generic version, the HADDOCK version, is going to have some overhead because it is generic, but we're hopeful that we can still capture that same speed up that MDDs provide. So as we see, we are comparing how many backtracks our search takes to get all solutions compared to the MDD's width. So in the dedicated implementation of an MDD propagator, we see that increasing the widths cause an exponential drop down in the size of the search tree. And this happens for all three of the constraint classes. So how does HADDOCK measure up? Well, for the first constraint class, we can see that yes, it does this beautifully, right? That we're still outperforming the classic version, and we're actually following that same curve the dedicated propagator has fairly closely. Sometimes there's a bit of overhead, and this happens for all three constraint classes, and sometimes, though, it's actually even better than the dedicated version. And this is all of those graphs together. If we want to compare the CPU time, we can see that again, as we increase the width, the dedicated propagator performs better. If we want to compare now HADDOCK, we can see that as we increase the width, we're seeing that same trade-off. We're seeing that same improvement from the CPU time. And again, sometimes HADDOCK performs a little bit slower, has a bit of overhead to dedicated, but other times HADDOCK is able to outperform. So, in conclusion, we have presented HADDOCK, which is a generic language for creating these MDD propagators. It does this in a way that mirrors CP models thanks to the composition of constraints. And while doing this, it achieves that same benefit that dedicated MDD propagators are known for while being generic. Our code was implemented in mini-CP and is available online, and it includes the specifications necessary for multiple different constraints, including all different among GCC, sequence, and sum. Thank you for your time.